I frequently have this kind of feeling. I think I understand. When I read something very frequently, I cannot quite understand. But still, I believe I think I understand. Speaking from my past experience, most of the time when I feel I think I understand, it later proved to be either an illusion or delusion or self-deception. What I am saying is that I think I understand always proved to be a false belief. So, whenever I feel I think I understand, I doubt myself if I really understand it. I have read several times about center of mass from Thomas's Calculus, 14th edition. I also have 10th edition of this book, and I read 10th edition about center of mass. From this book, in chapter 6, applications of definite integrals, moments, and centers of mass. I read this part of text several times, not just once, but at least 3 or 4 more times, very carefully. What I didn't quite understand in this book is this part. Sum of torques equals 0. At this line, I had such feeling. I think I understand, but I didn't quite understand it. So I also read Fundamentals of Physics about center of mass. This book also explains about center of mass. It is explained in detail like this. I read this part several times and I believed I think I understand, but that's not quite true. So I also referred to this book from part 1, chapter 9, section 6, the center of mass. I read this part of text several times. I had such feeling. I think I understand. But I had such feeling. Something is missing in this explanation. So I read James Stewart Calculus Early Transcendentals, 8th edition. From this book, chapter 8, section 3, Applications to Physics and Engineering. From this book, if you scroll down, you can find moments and center of mass. After reading this text, I finally understand center of mass completely, correctly, accurately, how this expression is derived. Such understanding about center of mass enabled me to solve from Thomas's calculus parallel axis theorem this problem here completely. In this episode, we will prove the parallel axis theorem and solve problem 35, proof of the parallel axis theorem. This part. Once we understand parallel axis theorem, we can solve wide range of problems related to rotational motion. Please understand that I got this explanation or center of mass from this book, James Stewart Calculus Early Transcendentals. The PDF book is 8th edition, but I have a hard copy 9th edition. My objective in this session is to prove parallel axis theorem. I got this problem from Thomas's Calculus. In the Thomas's Calculus, Chapter 15, Section 15.6, Applications. If you scroll down, you can find exercise 15.6. We are going to solve problem 35, the parallel axis theorem. Proof of parallel axis theorem. This is the problem we are going to prove. But as I said, I got this explanation from James Stewart Calculus, Chapter 8, Section Applications to Physics and Engineering, from Moments and Center of Mass. I got the explanation from this part of the book. This blue line is massless rod, or we will assume its mass is negligible. I will not use the term torque or gravity. Instead, I will follow explanation in the book. This is experimental fact discovered by Archimedes and called law of lever. Okay? Archimedes is a Greek in BC 200. At that time, gravity is a known concept. Now scroll up. This body M1 will create turning effect. This is counterclockwise. Counterclockwise turning effect. This body M2 will create turning effect clockwise. Note that the distance d1 should be greater than or equal to 0 from fulcrum, point of fulcrum. Also, d2, the distance from the fulcrum to the point of application. We call this point of application should be greater than 0. Don't forget this fact. If from the experimental fact discovered by Archimedes, M1 times D1 is equal to M2 times D2, if it holds, then this system balances. Then the system will balance. Just so you know, the fulcrum's point is called pivot. Some people pronounce it pivot or pivot or pivot. I will pronounce it pivot. The position of M1 is called point of application. So this position is also point of application. If you understand the terms, you can read your text. Now we will move this figure into coordinate system like this. So this pivot point now becomes x bar or COM, center of mass. M1 is here. This is the origin. X1 is here. M2 is here. X2 is here. From this equation, M1 times D1 equals M2 times D2. This is this expression. D1, D2 should be greater than 0. So M1 times, if D1 is greater than 0, we should subtract from x bar x1 equals M2. D2 should be greater than 0, so we have to subtract from x2 minus x bar. We move left side to the right. Then 0 equals minus M1 x bar minus x1 plus this term M2 x2 minus x bar. We distribute minus 1 to here and here. Then we have M1 x1 minus x bar plus M2 x2 minus x bar. So we have this result: 0 sigma m I x I minus x bar. We have this result. You can try with 3 or 4 or more points. You will get this result. Now we distribute 0 equals like this, Then sigma mi xi minus sigma mi x bar. X bar is constant, independent of I. So we can say sigma mi xi minus x bar sigma mi. Then we move this term to the left. We have x bar sigma mi equals sigma mi xi. Sigma mi is total mass and cannot be zero. Mass cannot be zero. So x bar equals sigma mi over mi xi. We have this result. Now, in this system, what if we place center of mass to the origin? What if we move center of mass to the origin? That is, x bar center of mass is 0. What will happen? Now scroll down. In this expression, if x bar or center of mass is 0, then 0 equals sigma mi over mi xi is 0. Since mi, the total mass, cannot be 0, we should conclude sigma mi xi should be 0. That is, if center of mass is 0, then this term is called the moment of the system about the center of mass should be 0. We need this concept from the definition of definite integration. This sum is called Riemann sum. So sigma I, it can be anything. 1 n mi xi should be alpha beta x dm when n approaches infinity. This is definition of definite integral. So we can say about center of mass x dm is 0. In 2D or 3D, we can say r dm equals 0. We need this concept to prove parallel axis theorem. In this theorem, we are going to prove this relationship. Show that the pulsed moment of a body in space about any plane through the body's center of mass is 0. Pulsed moment about y-axis my equals x dm is 0. Scroll up. In this diagram, this is y-axis. This represents my, moment about y-axis. So this is 0, about center of mass. We just proved this part. Show that the pulse moment of a body in space about any plane through the body's center of mass is 0. We proved it. Now the remaining part is rather simple. To prove parallel axis theorem place the body with its center of mass at origin. So center of mass is at origin. This vector is now from the line passing through center of mass. This vector is this vector from the axis of rotation through the center of mass, with the line center of mass along the z-axis and the line perpendicular to xy plane at the point h, 0, 0, 0. H is x coordinate from the center of origin. Don't forget this fact. Let the region of space occupied by the body. So D represent this body, the region of this body. Then the notation of the figure. This is definition of second moment. So this vector is this vector. This point is called point of application. Please try to remember the term. Also, this point is, I would call it pivot point. This vector is usually represented by R. This vector is computed by subtracting B in this direction. Then, like this, this vector is minus HI. So, this vector becomes minus HI plus V, or V minus HI, or Xi plus Yi. This is V from here minus HI, this term. Then we have X minus HI plus YI. I would write it R. So magnitude of R square is this vector V minus HI square. Now I L D, this integrand. So x minus h square plus y square dm. Then x square minus 2xh plus h square plus y square dm. Then x square plus y square minus 2hx plus h square dm. Then we can expand x square plus y square dm minus d 2hx dm plus h square dm. Then this term becomes ICM plus this term can be 2h xdm. This 2h xdm is 0. So this term becomes 0. This term h is constant. So h square dm over d, this is mass m. So it becomes ICM plus h square m. ICM equals x square y square dm. This is second moment or moment of inertia with respect to center of mass. So I L the moment of inertia with respect to line L, rotational axis, is moment of inertia with respect to center of mass plus h square m. H is the distance from the center of mass to the new axis of rotation. We proved this relation called parallel axis theorem. Good job.